If I were to approach you on the street and marvel at the Kelvin-Helmholtz instability, you'd probably look at me like I were crazy. Like, who are these guys and what are they destabilizing exactly? Well, thankfully, this theory is not nearly as complicated as it seems, and over the past couple years, I've been able to take fluid mechanics courses to better understand this phenomenon. So today, I'll walk you through the historical background of this instability, the physics principles surrounding it, as well as real-world examples of it. Because after all, this instability has evolved over time to become something necessary to understand how fluids interact with each other. So first, let's get into the historical background of this instability. Fittingly enough, according to a 2008 article by philosophy professor Lydia Patton, Kelvin, Lord Kelvin, and Hermann von Helmholtz pioneered this instability, as the name implies. They did so by sending letters back and forth to each other. They sent these letters about their latest scientific discoveries and the results of their studies, but unbeknownst to each other, they developed strikingly similar results to the scientific question as to how fluids behave, why they behave the way they do. And in synthesizing their papers and their studies and their lab findings, as a result, this instability was born. So it all started with two soon-to-be scientists sending letters back and forth to each other in the mid-1850s, which is pretty interesting, I think. So now before we get into the instability itself, let's look into the physics principles that'll provide us with some useful background. So first, what exactly is a fluid? Well, according to a 2001 report by mechanical engineering expert Richard Gentle, it's not just a liquid, contrary to what many believe, but it can also be a gas or aqueous solution, so long as it's able to move freely and doesn't have a defined shape, as shown by the image here. If it's not rigid, doesn't have a fixed shape, it's a fluid. So a gas could also be one, for example. So now, according to a 2019 journal published by civil engineering professor Chris Baker, there's also the continuity principle that surrounds this instability. It posits that the volume of fluid leaving a region is the same as the volume of fluid entering that region. Because we can't just have fluid appearing and disappearing out of nowhere. It has to be the same. So when we have a smaller pipe with a smaller cross-sectional area, in order to have the same flow rate as a bigger pipe, the fluid must be moving faster in the smaller pipe. So the two variables have to balance each other out. So when the area is bigger, the velocity is smaller, and vice versa. Otherwise, the conservation of mass would be defied, and that can't happen. So now, according to the Bernoulli Principle, and according to a 2019 instructional book published by Meave Shelton, the energy between 2 points in an unimpeded fluid remains constant. Unimpeded just means in this case that there are streamlines, there are no obstacles preventing a fluid from moving in a pipe, for example. And then the Bernoulli Principle here posits a relationship between speed and pressure. So when the speed is high, the pressure is low, and vice versa. So we have another balancing act happening here. And this makes sense because let's look at, for example, the middle region of this pipe. The speed of the fluid is high in this case, so it's moving really quickly. And if it's moving quickly, there's a very low chance it's going to make contact with the rim or the walls of the pipe. So there's less contact, less collision happening between the particles of the water and the wall, which means that there's lower pressure, and vice versa. So again, we have a balancing act here. So now that we have this background, what exactly is this Kelvin-Helmholtz instability? Well, it looks like this. It's like a swirling effect. In fact, it's often referred as a swirling effect. So it begins with a perturbation or disruption in the boundary between two distinct fluids. So the higher pressure fluid here moves up because fluids naturally want to move from a high pressure to a low pressure. Think about when you're cramming for finals, you don't want to be so pressured. You want to move to an area of lower pressure, so to speak. So it's kind of that same analogy. So because of these pressure differences and velocity differences, we have this turning effect. And then according to a 2017 video featuring Professor Mike Merrifield, he gets deeper into why this occurs by, again, reiterating pressure differences and how this makes the perturbation more drastic. So as I mentioned earlier, the fluid naturally wants to move from a high pressure to a low pressure. So that's why the middle region of this bottom fluid is going to move up because it's moving to a lower pressure region, then it's going to curl in on itself. So what are some examples of this now that we know what it is? Well, according to a 2014 article by research associate Valero Mara, fluctus clouds are types of billows, and these Kelvin-Helmholtz patterns occur because the cloud interacts with the air surrounding it and moves to an area of lower pressure, as mentioned earlier. And then Jupiter's Great Red Spot is one of the biggest, if not the biggest manifestation of this, as seen by the patterns here. This is actually twice the size of Earth, by the way, which is really fascinating. So it just gives you a sense of how large this actually is and where this instability surfaces. So what did we discuss here? Well, now we know that this instability started with some soon-to-be scientists in the 1850s sending letters back and forth. But through understanding the continuity principle and Bernoulli principle, we know that we can see this instability all around us.